Very good. So welcome everybody. So it's my pleasure to be here again to deliver this second lecture in the series regarding the Schrödinger equation. So last Thursday, I was presenting in a step-by-step basis what is the meaning of the Schrödinger equation. Today, I will focus my talk about how to solve the Schrödinger equations in very simple cases. But those are cases that will be related with different issues that will appear afterwards in the ASESMA school in Ghana. So we are going to solve the Schrödinger equations in three cases. The first one is the free electron gas that will be related with the lecture about plane waves or about the description in metals in the school. Then I will focus on the hydrogen atom, and this will be related with the pseudopotentials or with the lecture about using atomic orbitals as basis set. And then finally, I will talk about the quantum harmonic oscillator in one dimensional. And this may be related with some thermal properties. Again, as it happened last Thursday, I would highly encourage to take a look to this book by Daniel Fleisch about the basic meanings of the Schrödinger equation. So again, this is a very important and extremely recommended textbook for a newcomer in the field. Okay, so let's go to the first part of the talk that will be devoted to the free electron gas. So let's start with a very simple problem. Imagine that you have a quantum particle that is confined in a specific regions of space, and I'm going to call this region of space the potential well. So the potential well is a region where you have a flat potential, let's take it at zero, within a particular region that I will call between this region between, it will be located between x equals 0 and x equal a. And then at the boundaries, I have an infinite potential, okay? So that means that within the well, there is no force acting on the particle, and the particle is forced to be contained within the box by infinitely strong forces that appears at the edges of that region. So that's the meaning of the infinite rectangular potential well. So now our goal is how to compute the ground state of an electron gas that is made of m free electrons. And by free electrons, I mean that electrons do not interact between themselves nor with the lattice in one dimension, just to make the problem as simple as possible and just to fix the most important ideas. And the only interactions between the electrons is that we should keep the Pauli exclusion principle. Okay, so I will describe what this principle is in a few slides from now. So the starting point is just to solve the Schrödinger equation. So the first thing to do is to define the Hamiltonian. So in this particular case, the Hamiltonian will be made of the sum of the kinetic energy. And as I was explaining last Thursday, in one dimension, the kinetic energy is minus h bar squared divided by twice the mass of the electron, and then the second derivative with respect to the spatial coordinate twice. There are no potential energy within the box. There is no potential energy within the box in this case, so the potential energy term is zero. And then the time-independent Schrödinger equation, in this case, takes the simple form here, okay? And we have boundary conditions, and the boundary conditions is that due to the infinite barrier, the electrons cannot leave the crystal. That means that the wave function at x equals 0 and x equal L, where L is the boundary, and 0 and L are the boundaries of the box, then the wave function must be 0 at those points. And of course, the wave function has to be normalized. That means that the electron is somewhere within the potential box. That means that we can take the integral of the probability density within the box, it should amount to 1. So that's the problem to be solved. And now the question is whether you know a wave function then when you take, or a function that when you take the derivative twice with respect to the position, it goes to itself with a negative sign. And there are I can think about three of them. One of them is the sine, another is the cosine, and if you combine the two of them, you might have an exponential, a complex exponential function. Here, the sine function is the most valuable one because it easily complies with the boundary conditions. In particular, the shape of our eigenfunctions will be just a constant, that is a normalization constant, multiplied by a sine. But the point here is that not all the wavelengths are allowed. So only the wavelengths that are an integer number of half lambdas are allowed. So in this case, you can easily check how we can comply with the boundary conditions. So with a function of this shape here, the wave function is 0 at x equals 0, and it is also 0 at x equal L. Okay, and then the normalization constant, you take the modular square of this wave function, you integrate to the length of the box, and then you end up that this with the fact that this normalization constant is nothing else than the root square of 2 over L. And if you replace this wave function here in the time-independent Schrödinger equation, then you realize that the one electron energy levels take this form here, h bar over 2m, and then m pi over L squared. So you can see here how the energy is a quadratic function of an integer number m, and we can go slightly more deeply into the meaning of both the eigenfunctions and the eigenvalues. So the eigenvalues are the possible outcomes of energy measurements of the possible energies of a particle confined in an infinite wall square potential. And as you can see here, one very important conclusion is that not all the energies are allowed. In particular, the wave numbers associated with the energy eigenfunctions within the infinite rectangular well are quantized. Only some discrete sets of possible values are allowed and are given by the integer, possible integer values here of this number m. And the energy difference between adjacent wave functions increases with increasing this number here, m. So the wave function must have 0 amplitude at both edges of the well, and therefore the only allowed wave functions are those with an integer number of half wavelengths within the cell. So those are two important differences with respect to classical mechanics. So if you remember the possible solution for a particle in a box in classical mechanics, then all the positive values of the energy are allowed. And at 0 temperature, the lowest energy state has 0 energy, because at 0 temperature, the particle will be fixed, it's not moving. And then since the potential within the box is 0, that means that the total energy in classical mechanics at 0 temperature is 0. However, in quantum mechanics, there are two important differences with respect to the classical solution. So the first one is that the particle can take only certain values. The solutions are quantized, and at 0 temperature, the lowest energy state has a non-zero energy that is called the 0-point energy. In particular, this energy takes the value when it's the value where n is equal to 1, and it will take the value h bar squared over 2m pi squared over L squared. So we can take here a graphical interpretation of the different wave functions as a function of the energy. And here we can see how the lowest energy state, that is called the ground state, has a node. And by node, I mean a location of 0 amplitude of the wavelength at each boundary of the well. Okay, so at the ground state, the wave function has a node at x equals 0 and has a node at the other edge of the well, but there are no nodes within the well. However, for higher energies, that means usually they are called excited states, then each step up in energy level adds another half cycle to the wave function across the well and another node within the well. So if we go one energy up, we can see how we are adding another half cycle. So we have here 2 cycles, and we have 1 node within the well. If we go 1 step further, we have 3 halves of the wavelength, and then we have 2 nodes, and then so on and so forth. Okay. Another important characteristic of these solutions is that they alternate between even and odd parity if the center of the well is located here at the origin. So the ground state is odd, but then the first excited state is the ground state is even, the first excited state is odd, and so on and so forth. So they alternate the parity when we are moving up in energy. So another thing that we can get some flavor about is the relationship between the curvature and the energy. So as you see, as we move up in energy, the wave function is wiggling a lot within the well. So that means that the derivative is really high. That means that the Laplacian, or the second derivative, is really high, and that translates into a higher kinetic energy. So when we are moving high in energy, that means that we are expecting a large curvature of the wave function within the well. And that's one thing that is observed here in this figure. So it is very important to have in mind the relationship between the curvature and the energy in this problem. So now we have the solution, and now the thing is that we have to accommodate n electrons in these wave functions that are the solutions of my free electron gas confined in the box. So now we have to take into account the Pauli exclusion principle that tell us that there cannot be 2 electrons that have all their quantum numbers identical. And here, as a consequence of the Pauli exclusion principle, that means that each orbital, each eigenstate of my Hamiltonian, can be occupied with a maximum of 2 electrons with opposite spin. So therefore, there are 2 different numbers that allow me to label all the electronic or the possible states for a given electron. So one of the label is a positive integer that I'm calling n in the previous slides, that is telling me what is the if I am in the ground state or in the given excited state of my Hamiltonian. And then the second number that allow me to label the state of an electron, it is related with the spin that can take a value of positive or negative, okay, plus 1/2 or minus 1/2. So that means, just as an example, if I want to fill the box with 6 electrons, I am going to put 1 electron in the ground state with a spin up, another electron in the ground state labeled with n equal 1 with a spin down, and then this level with n equal 1, the ground state is filled. It's totally filled with electrons. So then the next electron must go to the first excited state. That means n equal 2 and spin up, and then the next electron will be will be allocated in the state n equal 2 with a spin down, and then the next one will go with to the next excited state, and so on and so forth. Okay, so that's how we are going to fill all the states up to the number of electrons that we are considering in our box. Okay, so we can wonder if we can go one step further in our model. And in particular, here I'm going to introduce another concept, that is the concept of the periodic boundary conditions. And this is based on the fact that we should expect that the bulk properties of a given system should be unaffected by the presence of the surface. So as soon as we move a few layers inside the material, then I can think that the system is forgetting about the existence of a surface. So the idea is that then a natural choice to emphasize the inconsequence of the surface is just disposing of it altogether. So getting rid of the surface. So how can we get rid of it? So imagine that we have here a simulation box that is made here of a few replicas of my unit cell. and this is extended along periodically along the different directions of space. So in this case, we can get rid of the boundary conditions, just making a band and assuming that we have these periodic boundary conditions. That means that the things or any property at a given edge of my supercell is exactly the same as in the opposite phase. Okay, so what is happening here in this surface that I'm on this part, in this edge that I am just pointing to with my pointer, is exactly the same as the opposite edge here, and the same happens in this direction. So you can consider here that it's like playing with an origami sheet of paper. So we can get rid of the effect of this surface if I bend my sheet of paper and then I am closing it in a cylinder as here. So essentially that's the meaning of the periodic von-Karman boundary conditions, okay? So the thing now is what would happen in my free electron gas if instead of solving it within a infinite potential well, I am assuming periodic boundary conditions. So in that particular case, the wave function, the wave or the time-independent Schrödinger equation will be the same as before. So I only have here the kinetic energy term, and then I apply the kinetic energy term to the solution or to the wave function, and then it has to be the same as an eigenvalue multiplied by the wave function. But now the boundary conditions are different, in the sense that if I am moving the equivalent of one side of the supercell, then I should get the same value as within the von-Karman supercell. Okay, so those are the three boundary conditions. So in this particular case, the solutions are traveling plane waves. Okay, so they have the shape of a plane wave here that is normalized with this factor that goes with 1 over the volume of my von-Karman supercell. So in contrast with the stationary waves that we were studying before, where the wave function vanishes at the edges of the well, here these traveling plane waves represent better the transport of electronic charge. So these solutions look like plane waves characterized by a wave vector k that, as you can see here, they are normalized to the volume of the von-Karman supercell. The energy, the corresponding energy, it takes a shape that has h bar squared k squared divided by 2m, where k squared is the modulus square of the wave number k here. Okay? So this is the first time that a plane wave appears, and a plane wave is a very important solution because they are the basis of many, many different codes implemented within the DFT theory. So a plane wave, I am representing here a few of them. A plane wave is a wave where the wavefronts are planes. That means that the amplitude of this plane wave is constant in any plane that is perpendicular to the wave vector k, and they are periodic in the direction parallel to k with a wavelength that is lambda. And lambda is nothing else than the de Broglie's wavelength, that is 2 pi over lambda. So here I am plotting a very simple case. Let's take the plane wave that is directed along the y direction here, and we can see how any point contained in this plane here has a constant value, because any r, any vector r, any position vector r here is perpendicular to k, and that means that the dot product between k and any r contained in the plane takes essentially the same value. And the same happens to whatever other plane represented here by these planes that are perpendicular to the k vector. Okay, so the dot product between any r, any position of this plane, and k is constant, and therefore the plane the wavefronts are planes. And these plane waves are periodic in this particular case. They will be periodic along the y direction with a periodicity that will be 2 pi, where k is 2 pi over lambda. So those, as I was telling you before, those plane waves will be very important in density functional theory, and there will be a lecture on this during the ASESMA school. Okay, so we can move to the second problem, and the second problem is the hydrogen atoms that will play an important role in the theory of pseudopotentials. For instance, how to solve the Schrödinger equation for an isolated atom. It will take an important role while generating pseudopotentials, or when we are going to use atomic orbitals as the basis of our solutions in the DFT codes. So now, as the first thing to do, as before, is just to write the Hamiltonian for one electron in the hydrogen atom. And again, my Hamiltonian operator will be the sum of a kinetic energy term plus a potential energy term. So the kinetic energy term is p squared over 2m, where p is the momentum operator. Then it takes the form of minus, the p squared takes the form of minus h bar squared over 2m multiplied by the Laplacian. So this is the same term that we had before for the particles in a box, or for the free particles with periodic boundary conditions. So this thing is the same as before. But now the difference is that instead of having a potential that is 0, we have the Coulomb potential between the proton and the electron. So this is an attractive potential. That's the origin of this minus sign here. And it takes the shape of a Coulomb operator. That means the E squared, where E is the electronic charge of the electron divided by 4 pi epsilon 0 r, where r is the distance between the electron and the nuclei. So therefore, my Hamiltonian and my Hamiltonian operator takes the shape that is here. Due to the symmetry of my problem, it is very useful to use spherical coordinates, because my problem has angular symmetry. So essentially, all the angular directions are the same, and the only important magnitude here will be the distance between the electron and the nuclei. Another important thing that we can do is just to use this reduced mass. Essentially, this is related with the fact of solving the problem of a particle with a reduced mass that is going to move around the center of mass of the system. In this particular case, since the mass of the proton is much larger than the mass of the electron, this reduced mass is pretty close to the to the mass of the free electron. As you see, the difference is only 5 parts in 10,000. And essentially, mu, that the reduced mass, and the mass of the electron are basically the same. And this helps me to enter, or to make the notation simpler, because I'm going to use this m symbol for another quantity afterwards. So now, introducing this reduced mass mu instead of m, this is my time-independent Schrödinger equation for the hydrogen atom. So I have the Hamiltonian here that applies to the wave function c, and then this would be equal to the energy, again, the times function. So that's, we can rearrange a little bit the terms, and I can write my Schrödinger equation like this. And the only thing that is a little bit more cumbersome is that using polar spherical coordinates, the shape of the Laplacian operator is a little bit more difficult than before. So the shape of the Laplacian operator in spherical coordinates takes the shape that is, you can see here. So it looks like slightly more complicated than in Cartesian coordinates. And the shape of the time-independent Schrödinger equation for the hydrogen atom in spherical coordinates takes this shape here. So I'm not going to enter in the details about how to solve this, because it will take a couple of hours to go step by step. But the most important message is that this equation can be solved by separation of variables. And in particular, the wave functions can be considered as the product of a radial part times a function that only depends on the angular variables. And these functions that only depends on the angular variables here are the spherical harmonics, okay? So I have here, I can label the different states of my system with three different quantum numbers: the principal quantum number n, the angular quantum number L, and the magnetic quantum number M. Okay, and they depend on the position that is written here in polar spherical coordinates, so r, theta, and phi. And then I can consider that the eigenfunctions of my hydrogen atom can be written as a radial function here multiplied by a function that depends only on the angular coordinates, and those functions are the spherical harmonics. Very importantly, due also to the symmetry of the problem, that means that my potential is central. It only depends on the distance between the electron and the proton. Then, due to this symmetry, the eigenfunctions of my Hamiltonian are also eigenfunctions of two important operators. So one of them is the modulus square of the angular momentum, and the other is the component of the angular momentum along one particular direction that I'm calling zeta. Then I have here the exponential that, as I was explaining you last Thursday, this is related with the solution of the time-dependent Schrödinger equation that factorize in a part that depends only on the position and a part that depends only on time. So one important message here is that, as before, as in the case of the particle in a box, not all the energies are allowed. So the energies are quantized. And for the case of the hydrogen atom, they depend only on this principal quantum number n with this, and they evolve with this shape here. And another important message is that the ground state, that means for n equal 1, it takes this value here that amounts to minus 13.6 electron volts. That is also taken in some cases as the unit of 1 Rydberg. Okay, so that's 1 Rydberg is the energy of the ground state of the hydrogen atom. Another thing that we can get from this, from the quantization of my of the solutions of my energies, is that the possible transitions between different energy levels in the hydrogen atom. So here there are different families depending on the origin of the initial state and the final state. So we are going to, from an excited state with an n that is larger than 1 to the ground state. So if the transition is from n different from 1 to n equal 1, we have the Lyman series. If the transition is to the n equal 2 state, we have the Balmer series, and so on and so forth. Okay. So I am not in this talk, because this will be out of the scope of this talk. I have not talked about the how to go step by step in the solution of this. If you are interested, you can take a look to this very, very nice tutorial that was prepared by Richard Behiel, and then if you click here, you can get you can go directly to it. And here I would like also to point to a very, very interesting video prepared by a YouTuber, a Spanish YouTuber, that is the name is Quantum Fracture. It takes only 6 minutes, so I think it's a very good exercise if we can take a look to it. So let me because it's very, very instructive. So let me just. So can you see my screen?
Yes.
Okay. So let's take a look to this video. It's in Spanish, but I will translate it into English. So let me check here. Subtítulos. Okay. So it takes 6 minutes.
Sea el mito más extendido de toda la física, que los átomos tienen esta pinta. No, esta imagen del átomo es una antigualla que llevamos arrastrando los últimos 100 años. Y entiendo por qué. A nuestro cerebro de simio le cuesta mucho menos identificar un átomo utilizando diagramas como estos que mostrándole la extraña vida real. ¿Qué demonios? Si yo soy el primero que los usa. El problema es que si los átomos fueran exactamente así, no estaríamos aquí hablando de ellos. Veréis, este modelo planetario del átomo, donde los electrones giran como bolitas alrededor del núcleo, fue propuesto por un físico neozelandés llamado Rutherford. Y en su momento fue todo un descubrimiento, pero la peña no tardó en encontrarle problemas. El más grave, su estabilidad. Imagínate que tienes una rueda de bicicleta, la impulsas para que gire y la metes dentro del agua. ¿Qué le va a pasar a la rueda? A medida que gira, irá removiendo el agua que tiene a su alrededor, emitiendo pequeñas olas. Poco a poco pierde su energía y se para. Algo parecido le pasa a los electrones del átomo de Rutherford. Al estar acelerando dentro de un campo electromagnético, van perdiendo energía emitiendo radiación. Perder energía significa quedarte cada vez más parado, y quedarte parado mientras orbitas significa caer en espiral rumbo a chocarte contra el núcleo. Vamos, que si nuestros átomos fueran como los de Rutherford, estaríamos más que muertos. Físicos como Bohr, Sommerfeld o de Broglie intentaron arreglar los problemas del átomo de Rutherford utilizando ideas de vanguardia, pero no fue hasta que Schrödinger, utilizando su última creación matemática, resolvió casi todos sus problemas de una. ¿Qué era lo que fallaba en la idea clásica del átomo? Un pequeño detalle. Un átomo está hecho efectivamente de electrones girando en torno a un núcleo. La cosa es que giran de manera cuántica. Las reglas del juego de los electrones no son las mismas que a las que estamos acostumbrados, son las reglas de la mecánica cuántica. Hemos hablado ya varias veces en el canal sobre esta vaina, pero, como recordatorio, una de las grandes diferencias entre el mundo cuántico y el que experimentamos todos los días es la indeterminación. Los objetos cuánticos, como los electrones, no tienen por qué estar en un lugar del espacio concreto o moverse a una velocidad exacta. La mayoría de veces, estas cantidades están indeterminadas, no tienen un valor específico. Girar es una de ellas. Por eso, la manera correcta de visualizar al electrón girando no es a través de una órbita, no es una bolita que sigue un camino. La realidad cuántica es que dentro del átomo, la posición del electrón está indefinida en un montón de lugares del espacio. Esta indeterminación espacial la representamos los físicos a través de esta nube. De hecho, técnicamente, esta es la función de onda del electrón dentro del átomo, pero normalmente se la llama orbital, la evolución cuántica de la órbita. Ojo, que el orbital no es el electrón desparramado como si fuera agua. Hasta donde sabemos, los electrones son como puntitos. Lo que los orbitales reflejan es el grado de indeterminación en la posición que tiene el electrón. Nos chiva los lugares en los que hay más probabilidad de detectar el electrón si le forzamos a definir su posición. Repito, cuando nosotros lo forzamos. Lo normal es que su posición esté indeterminada dentro de la nube. Y lo más bello de todo esto es que el electrón puede vivir indefinido dentro del átomo de maneras muy distintas, dándole al átomo formas asombrosas. Vamos a explorar las del átomo más sencillo de todos, el átomo de hidrógeno, aunque lo que vais a ver aquí se puede extender más o menos a toda la tabla periódica. La forma de los orbitales, básicamente, depende de 4 factores, 4 números que etiquetan cada manera que tiene el electrón de moverse dentro del átomo. Os presento los números cuánticos y agarraos, que esto se va a poner muy loco. El primero, llamado n, marca cuánta energía tiene el electrón. Cuanto más alto es n, mayor energía. El último factor lo dejaremos para otro vídeo. Classic Quantum Fracture. Y los otros dos son propiedades del giro. El segundo número, L, marca la cantidad de momento angular que tiene el electrón, mientras que el tercero, M también marca la cantidad de momento angular, pero en una de sus componentes cartesianas. Ya lo sé, esto ha debido sonar muy a chino, pero tenía que decirlo con cierta precisión, y es que no hay una manera intuitiva de presentarlos. Girar cuánticamente es un movidote que no se parece en nada a la idea de girar a la que estamos acostumbrados. Bueno, si los átomos fueran como pensaba Rutherford, te diría que L, el momento angular, expresa lo rápido que gira el electrón o lo grande que es su órbita, y que M, digamos, la inclinación de ese momento angular, determina cuál es el eje en torno al cual el electrón rota. Sin embargo, en el mundo cuántico estas explicaciones se desdibujan. No puedo deciros que el momento angular refleja lo rápido que va el electrón cuando ni siquiera tiene su velocidad determinada, o que M refleja el eje de Ciro cuando ni siquiera gira en torno a un eje. De hecho, incluso el propio átomo te muestra lo absurdo que es pensar de esta manera clásica. Veréis, el estado menos energético de todos en los que el electrón puede estar, en el que el electrón está más tranquilo, es en el que L vale 0, lo que clásicamente querría decir que su velocidad de rotación es nula. Es decir, que según la mentalidad clásica, hay átomos en el universo en el que el electrón ni siquiera está girando, haciendo esta imagen aún más inexacta. Los físicos muchas veces utilizamos estas explicaciones clásicas como muletas, una forma de ayudar a nuestro cerebro con estas imágenes antiintuitivas del mundo. Pero en el fondo de nuestro corazón sabemos la verdad, que L y M reflejan cosas muy abstractas y muy profundas, de las que hablaremos en otra ocasión. En cualquier caso, os dejo aquí con unos cuantos orbitales para que podáis ver lo preciosos que son los átomos de verdad. Disfrutadlos. ¿Verdad? Os dejo en la descripción una web en la que podéis verlos todos y experimentar con ellos. Y recuerda, si quieres más ciencia solo tienes que suscribirte. Y gracias por verme.
Okay. So hope you have been able to follow this presentation. Now, okay, so can you see again my screen with the presentation?
Yes, it's clear.
Okay. So then let me continue with the last example. So the last example is the quantum harmonic oscillator in one dimension. So this is a very, very important problem, not only from the quantum point of view, but also from the classical point of view. In the next few slides, I would like to emphasize the importance of this harmonic approximation. So imagine that you have a potential, whatever. But the most important thing here is that this potential that I'm considering has a minimum at a given position that I'm calling here x naught, okay? So this potential may be, for example, the interaction potential between potential energy between two non-polar molecules as a function of distance. So if the molecules are very close one to the other, there is a very strong repulsion between them that prevents the overlap between the two molecules. If they are very far away one from the other, then the force is essentially equal to 0. And for some regions here, there is an attractive interaction potential between the molecules, and then there is an optimum distance here where the energy is the interatomic or the intermolecular potential is a minimum here. So imagine that we are interested in what's happening here only around the minimum. Okay, so if we are interested only of what's happening here on the minimum, then we can approximate the potential via parabola. That means that the displacements are not very large here around the minimum, the force is proportional to the displacement, and that gives rise to the equation movement of the harmonic oscillator. So you can think here, when you take a look to the original interatomic potential in black, or to the harmonic potential in red, you can say, okay, they don't look like the same. That's true in this scale, but if you take here the zoom around the minimum, then you can see how, here I'm just zooming around the minimum, you can see how the red curve and the black curve are pretty much the same thing. So from a mathematical point of view, you can consider here a potential in one dimension. So this potential is Vx, and then we can take a Taylor expansion of this potential around the minimum, okay? So this will be a constant, and then a constant A, and then here I have the first derivative of the potential with respect to the spatial location evaluated at the minimum, and I'm calling this term V, multiplied by the distance to the minimum. And then I have here 1/2 of the second derivative of the potential with respect to the position twice, evaluated at the minimum, I am calling Z, multiplied by the distance to the minimum square, and then so on and so forth with higher terms. Remember here that A, B, Z, D, and so on and so forth are not functions. They are just numbers. So A is the potential evaluated at the minimum, B is the first derivative evaluated at the minimum, Z is the 1/2 of the second derivative evaluated at the minimum, and so on and so forth. So now the point is that if we are at the minimum, by definition of minimum, then the first derivative is 0, and then we are getting rid of this linear term here, okay? And then if we are assuming that the displacement around the minimum are very small, that means that x minus x naught is small. The terms that goes with the third power and onwards can be considered to be much smaller than the second order terms. That means that I can just, I can consider that the terms from the third power on vanishes, and then I can just retain here in the expansion only the quadratic term. And that means that I can approximate whatever potential, it doesn't matter. If we are just moving around the minimum, then I can approximate it with this parabola here. But this parabola is nothing else than the potential energy of a spring, of an harmonic oscillator. So that's the powerful of this harmonic approximation is that ubiquitous in many fields when we are moving around the minimum, and that's why this problem is so important in physics. So in the case of one dimension, then the potential energy, just summarizing the previous slide, the potential energy is proportional to the distance of the object from the equilibrium position, to the square of the proportional to the square of the distance of the object from the equilibrium position, and then the constant of proportionality is related with this k here that is called the spring constant. And this spring constant is the force on the object per unit distance from the equilibrium position. So if we just plot the shape of the harmonic potential, it takes this form here, and it is you can consider that it's more difficult than the potentials that we were discussing at the beginning of this lecture, because the depth, let's call it the depth of the well, changes continuously with the position. It's not just 0 as it was in the infinite square well potential. Now the potential is changing with the position. Another important thing is that the potential becomes infinite when x tends to infinite, and that means that the wave function must be 0 in regions in which the potential energy is infinite, and then this determines the boundary conditions for the wave functions of the quantum oscillator. In particular, the wave function that we are going to obtain should decay to 0 if x tends to infinite. Now, as before, the next thing to do is to write the one particle time-independent Schrödinger equation that now takes this shape here. Again, we have the kinetic energy term here, plus the potential energy. And the potential energy now is this 1/2 of k x squared. And then we apply the Hamiltonian to my wave function psi. And then this must be equal to the eigenvalue E times the wave function psi. So in many cases, this time-independent Schrödinger equation is written in terms of this angular frequency omega that is defined as the square root of k over m. So just after a little bit of mathematics, I can transform this equation here, and I can write it in this form here. Okay, so this is essentially the information here is the same thing as here, but slightly rewritten. Okay, and now I have to solve for this. And as it happened with the case of the Schrödinger equation for the hydrogen atom, I will the solution of this, or how to solve it, is going beyond the scope of this talk. But the only thing that I'm going to tell you here is that there are two approaches. One of them is the analytical approach that make use of a power series, or the algebraic approach that make use of factorization and uses a type of operators that are called ladder operators. So if you want to take a look to a more precise or about how this equation is solved in a more precise way, you can take a look to the book that I was pointing at the very beginning of this talk. So now let's go directly to the shape of the wave functions and the values of the log values for the energies. And then after solving the equation, we can see how, again, the possible values of the energy are quantized. And now they take the possible values of n plus 1/2 h bar omega, where this n is an integer number. And that means that for the ground state, that means n equals 0. The ground state energy is not 0. The ground state energy of the system of this quantum harmonic oscillator in one dimension takes the value of 1/2 h bar omega. And now another important consequence of this of the shape of the eigenvalues here is that the space in between energy levels in the quantum harmonic oscillator is constant. That means that each energy level is precisely h bar omega higher than the adjacent energy level. So that's regarding the eigenvalues. So what about the eigenfunctions? So the eigenfunctions take this form here, where this capital H here are the Hermite polynomials, and the value chi that I am writing here is a way of rescaling the positions to make the solutions easier from the analytical point of view. So those C that I am writing here as the independent variable of the eigenfunctions are nothing else than the position divided by rescale by this reference position that is nothing else than the square root of h bar divided by m omega. So this is just a way of rescaling the positions to make the problem more easy from the mathematical point of view. So we can take a look. So this look like relatively complex with these Hermite polynomials and things like this, but we can take a look to the shape, to the graphical shape of these solutions. And here we are, the first eigenfunctions of the harmonic oscillator. So here we can see how they are equally spaced. So when we are moving up in energy, the distance in energy, the difference in energy between one level and the previous one is constant. And then we can see how the parity of the eigenfunctions is also changing, alternating between even and odd, even for the even ends and odd for the odd ends here in the solution. We can see how the quantum eigenfunctions just oscillate on the classically allowed region. And in this region, the curvature of the wave function increases with increasing the energy, as we were observing before also for the infinite square well potential. Remember that the curvature here of the wave function, it means that the derivative is higher, the Laplacian is higher, and then the kinetic energy is also higher. So we can see how if we increase the energy, we observe more cycles between the classical turning points that are located here at the crossing point of the energy with the potential. And then the quantum wave functions decay exponentially in the classically forbidden region. So this is another important difference with respect to the classical solutions. So if instead of plotting the wave function, I am plotting the probability density, remember that the probability density is related with the modulus square of the wave function. I have this behavior here. So we can see how at low energies, the behavior of the harmonic oscillator differs significantly from the classical one, in the sense that if we make a measurement of the position of the particle in classical mechanics, I would expect that the object will be located closer to the classically turning points, because the velocity of the particle at the turning points is smaller, and that means that the object spends more time there. However, here in the ground state, you can see how the probability density is higher at the center of the harmonic potential, and that's a difference between the classical solution and the quantum solution. However, if we are moving higher in energy, we can see how for excited states with higher M, the locations with or the probability of finding the particle in a position closer to the turning point here increases. And in particular, if N is getting very, very large, then we are recovering essentially the classical solution. So this is in agreement with the correspondence principle that I was talking about at the end of my first talk last Thursday. So finally, let me plot here another movie with the evolution of the real part and the imaginary part of the wave functions of some energy eigenstates. So the ground state is here, the first excited state is here, the second and the third. Here at the top, you have the classical movement of a particle with attached with a spring. And then here you have again the evolution in time of the real part and the imaginary part of wave functions of some states that are not eigenstates. In particular, they are coherent combinations. H is a coherent combination of states that look like more to the classical solution. But then you can see here how the speed about or how this real part and the imaginary part is changing depending on the frequency omega that appears here while solving the time-dependent Schrödinger equation. Remember that we have always this term here, as I was discussing last Thursday. And how the probabilities here with an increasing M, the probabilities of finding the electron in closer to the turning point increases, and how there are some points here that some nodes where it will be impossible to locate the electron. So with this, I am finishing the 3 examples that I wanted to discuss today. So next Thursday will be devoted to questions and answer session. And for that, I would like to ask you a favor, is that if you can pose a question well in advance, just in case I need to prepare a figure or to prepare some extra documentation for the discussion. So when we are discussing here online, it's very difficult to plot something or to derive a particular demonstration. So it will be extremely helpful if you can send me your questions or your things that you are more interested in and that you are not totally captured, if you can send me your question well beforehand, so I will be able to prepare extra documentation on this. So thank you very much for your attention, and then I will be happy to take your questions today. So you can send the questions to my email. So I'm going to write my email here in the chat.
Yeah, there is someone who raised his hands. Javier.
Okay.
Adiwele, can you unmute yourself and ask the question? Can you hear me, Adiwele?
Good afternoon, Prof. Thank you for the lecture. I actually wanted to ask where we could drop the questions, and I realized that you already dropped your email. That's why I lowered my hand.
Okay.
Thank you, Prof.
So there is another questions by Damilare that is taking, how do we relate the quantum harmonic oscillation to the molecular electrostatic potential to explain the electrophilic and nucleophilic sites of a molecule? Well, I'm not an expert on these electrophilic or nucleophilic sites of the molecule. The thing that I wanted to stress here is that this harmonic potential or this harmonic approximation appears very frequently in physics and engineering, when every time you are looking at a potential and then you are interested in what's happening around the minimum. Okay, so in that case, this harmonic approximation appears in many different fields. So then there is another question by Michael Isaye that is saying, how do we use quantum mechanic equations to discuss properties of a half-full Euler alloy? So this is not only related, I mean, quantum mechanics is used to compute the essentially the possible eigenfunctions of the system. Okay, and then once you have the eigenfunction, then you can, in principle, you can have access to all the properties of that system. The only thing that you have to do is to compute the expectation value of the particular operator that is related with the property you are interested in for the particular wave function. Okay, so this is a very complex problem in the sense that in principle, the wave function is a many-body function, and this is very, very time-consuming and very expensive to compute. So the thing is that we can get use of density functional theory that just change the problem to something that is more affordable. And then from the, I mean, within density functional theory, you can get very easily different properties like the structural properties of some of the electronic properties or transport properties and things like this. Okay, so that's the question by Michael Isaye. I would say that's the full topic of the ASESMA school. Okay. There is another question by Dada Oluwadamilare that is saying, why are we using two-dimensional two-second order derivatives for the time-independent Schrödinger equation? Okay, here the point is that for the time-independent Schrödinger equation, we need to compute. The first thing to do is just to have the shape of the Hamiltonian. So the Hamiltonian has a kinetic energy term and then a potential energy term. And the kinetic energy term, you can write it as p squared divided by twice the mass. And then if you take p, this is the momentum operator in quantum mechanics, p is minus I h bar nabla. Okay, so when you take this operator twice, to the square, sorry, then it appears the Laplacian. And the Laplacian is related with the second derivative with respect to the Cartesian, the second derivative with respect to the Cartesian directions. Okay, so that's how these second derivatives appear in the time-independent Schrödinger equations. So that's there is another questions by as by David Mahapane that is saying, what is the role of the ladder operator in solving the Schrödinger equations for the harmonic oscillator? Okay, so the ladder operators is an alternative to solve the time-dependent Schrödinger equations for the quantum oscillator. So essentially, they are related with the creation and annihilation of particles in a given state. Okay, so this is an alternative way. Unfortunately, I have no time to go through this in deep, but there is a way to write the position and the momentum operators in terms of this creation and annihilation of particles at different states. And then just using the eigenfunctions of these creation and annihilation operators, then you can get you can arrive to the same information as we have done now with or the same information that I'm showing you with the power series. Okay, so if there are no further questions today, then I would strongly,
So,
yeah.
sorry for coming. Yeah, because we want to receive the question, we can send by email for be thoroughly discuss it. What do you
Okay.
think?
Yes, so just feel free to send me your questions, and then I will try to find the most appropriate way to prepare extra documentation to address the different questions that you might have.
Yeah, thank you very much. Thank you very much for
Sure.
your time, and thank you very much for the nice talks and presentations, Professor Javier. So colleagues, please let's meet exactly next week by this time and then please send your questions as possible as early as so that to be addressed well. So thank you. Is there any information Javier you want to say, or we
No,
can
no.
close?
We can close here.
Yeah. So have a nice day. So see you next week. Please.
Okay, thank you.
And thank you very much again.
Thanks to you.
Yeah.